Hello and welcome back to Nunley Math. I'm your host, Aaron Nunley. Thank you so much for joining us as we talk about solving systems by substitution. This is the second of the three methods that we use in Algebra 1 for solving a system of linear equations. Now in my class, we've already talked about solving systems by graphing. I've actually not put a video up for that one, but I've got it almost ready. So if you do not already know how to do that, or if you haven't had a chance to check that out, make sure you check back very soon. We'll have that video up and running for you as well. Since my students have already covered this, if we were doing this in my class, I would begin with a quick review of solving systems by graphing. If you have not learned this yet, this may be sufficient to get you going. It's not an overly complex method. If not, come back and check out the other video. I would recommend, though, that if you think you know what you're doing, that you pause this video and that you try graphing these on your own first, and then playing the video to see if what you've done makes sense or not. For the sake of keeping this brief, though, I am going to go ahead and I'm going to do this fairly quickly for you, believing that you've already done that on your own. Notice that a system of linear equations is two or more linear equations that are in the same variable. In this case, I'm using x and y, that work together to help us solve a problem. So what I'm going to do is I'm going to graph this first linear equation, and I'm going to graph this second linear equation. I'm going to take a look at what happens when I put them both on the same coordinate plane. Since this first equation is in slope-intercept form, I am going to start at my y-intercept, which is the coordinate 0, 2. And I'm going to use that slope and go up 1, right 3, since those are both positive. And that's going to give me my second dot. And I'm going to continue that pattern as far as I can to the right. And then, of course, I can do that to the left as well, because negative 1 over negative 3 is also 1/3. That's down 1, backwards 3. And I draw a line of best fit that goes through there. I call it a line of best fit. It actually fits perfectly because this is perfectly linear. Notice I have a second equation, y equals 2/3 x plus 5. I'm going to begin this graph at 0, 5, my y-intercept. This one has a slope of 2/3, which says every time we go up 2, we're going to go to the right 3, up 2, right 3. I can also do down 2, backwards 3, down 2, backwards 3. And then I draw my line for that graph as well. Notice that every point on that blue line is a solution to our first equation, this one right here. Every point on that red line is a solution to the second equation that you see right here, but this point is special because out of the infinite number of possible solutions on the blue line and the infinite number of possible solutions on the red line, that one point, that 9 should be -1, that 9, -1 is the only point, wow, I said 9, -1, -9, -1 is the only point that they both have in common. In other words, if I put a -9 into the first equation, I get a -1. If I put a -9 into the second equation, I also get a -1. Because this works in both equations, we would say that it is the solution to the system. This second system we have over here, we're going to do the same thing with this one. We're going to graph it. Notice that this one, however, is not in slope-intercept form. These are both actually in standard form, where you have ax plus by equals c, which means probably slope-intercept is not our best bet for graphing those. Probably we're going to want to do this by graphing the intercepts. Notice that if you stick a 0 in for y and were to simplify, -4 times 0 becomes a 0, leaving you with x equals -4. So if 0 goes in for y, -4 would be the x. If instead of doing that you put a 0 in for x and solve, you would get -4y equals -4, and divide both sides by -4, you get 0, 1. Our focus here is not solving or graphing by intercepts, so if you're struggling with what we've just done there, you may want to go back and watch our video on that. For now, let's just go ahead and say that we can do the same thing with this second equation. If I put a 0 in for y, -3x equals 12, divide both sides by -3 and you get -4. Or alternately, you could put a 0 in for x. That would make this a 0, -4y equals 12, meaning you get 0, -3. If I graph -4, 0, and I graph 0, 1, that's enough points for me to see this line. If I graph -4, 0 and 0, -3, that's enough points for me to see this line. Notice that each of those has an infinite number of possible solutions, but only this point right here, this -4, 0, would work in both equations. Our last system, 3x plus 2y equals 0. I'm going to go ahead and switch that to slope-intercept form. I did that very quickly. Remember, we can subtract 3x from both sides using the property of equality and divide both sides by 2. Again, this is not our focus for today, so if that was a stretch for you, you may want to go back and look at rewriting equations in slope-intercept form. When I graph that, notice that in slope-intercept form, this is -3/2 x plus 0. So I start off at 0, 0. I'm going to go down 3, right 2, down 3, right 2. And I'm going to continue that pattern until I get this line. Our second linear equation is already in slope-intercept form, so I'm going to start off at -1 on the y-axis, and I'm going to go up 1 over 2, up 1 over 2, and so on and so forth. Notice that the solution to that system is right there at the intersection of those two lines. Now, I know what you're probably thinking. What is the solution to that system? I can be honest and tell you I really do not know. I put this on here because it illustrates a particular problem for us. You know, I could probably estimate this, and it's probably somewhere around 1/4, -3/4. But there again, that's just looking at it, inspecting it visually. It's not very exact, involves a lot of estimation and rounding. But it does point out for us one of the problems with solving systems by graphing, and that is this. If you don't get integers as your solutions, then you end up having to guess or estimate. Definitely not ideal. There are a couple other reasons we don't particularly like to solve systems by graphing. One being if the numbers are too large, they may not actually fit onto your grid paper. So I could have a solution to this system that is positive 1,000, -700. And who's really going to want to take the time to graph that? If you did try and graph that, you probably would have to use a scale other than 1, 2, 3, 4, 5, which means you're going to run into more issues of things that are hard to see because they're going to come in between the grid lines. Lastly, if you don't have grid paper at all, solving systems by graphing certainly is problematic. So what we do is we actually have two other options available to us. One we're going to learn about in this video, that's solving by substitution. The other we're going to learn about in our next video, which hopefully I will have up for you tomorrow or the next day, just as quickly as I can get to that. Both of those methods are pretty effective, but they have different scenarios where they're more useful than others. I think you're actually going to like these other two. The first method, the substitution method, relies on this basic idea. If two things are the same, you can swap one for the other at any time. So let's say I were trying to bake cookies, and the recipe calls for 1 cup of sugar, but I can't find my 1 cup measuring cup. There are other things that I could use instead. For example, we happen to know that 16 tablespoons of sugar is the exact same thing as 1 cup of sugar. So if using 1 cup was inconvenient or difficult for me, then I could use 16 tablespoons instead, and it wouldn't be a problem because it's the exact same thing. It's the idea of substitution. As long as they have the same value, or as long as there's the same amount of sugar there, it really doesn't matter which method I use for measuring that. Alternatively, you could look at it this way. If I'm going shopping and whatever I buy happens to cost $20, when I get to the cash register, if I reach into my pocket and pull out 2 $10 bills, the cashier's not going to freak out on me or think I'm crazy or anything like that. That's going to be perfectly acceptable because 2 $10 bills has the exact same value as a $20 bill. I can substitute one for the other without any problems. I could do the same thing with 4 $5 bills. 4 $5 bills has the exact same value as 2 $10 bills or as a $20 bill, but the cashier's not going to think anything of it because they have the same worth and can be swapped in and out and vice versa. And I know what you're thinking. He's not crazy enough to really go ahead and do this with dollars, is he? Oh, absolutely I am. If I were to give the cashier 20 $1 bills, they probably wouldn't like it very much. They probably wouldn't appreciate having to count all of those out, and it would probably inconvenience them at the end of the night when they had to balance out the drawer in their cash register, but certainly they would accept it as a substitute for a $20 bill because we know that all of these sets of money, all these groups of money have the exact same value. A $20 bill is the same as 2 $10 bills, is the same as 4 $5 bills, is the same as 20 $1 bills. Since they have the same value, I can swap one out at any point I want to for the others. Now we could also talk about mixing a 10 with 2 5s or a 10 of 5 and 5 1s, but I think you should be getting the point at this point. So I'm just going to move on from here. Here's what that looks like for us algebraically. Suppose I have two linear equations in a system. X plus y equals 6 and x equals y plus 2. Now you'll notice I've color-coded this for you because I wanted you to see this, this idea that when you have an equal sign in between two mathematical expressions, you are saying that those two things have the same worth or the same value. Just like a $20 bill has the same value as two $10 bills, when I see x is equal to y plus 2, I'm saying that this x right here and this y plus 2 have the same value and they can therefore be swapped for one another. They can be swapped in and out for one another. So if I begin with this first equation right here, this x plus y equals 6, notice I've gone ahead and I've colored the x red because I want us to recognize that I'm going to take this x and I'm going to replace it with a y plus 2. Since x and y plus 2 have the exact same value, I can take an x out and replace it with a y plus 2 anytime I want to. Now, what's the benefit of doing that? Well, when I was dealing with these two equations, they both had two variables. Earlier in the year, we discussed the fact that the more variables you have in an equation, the harder it is to work with. So we've been trying to keep our equations down to single variables. But these both had two. When I used my substitution method, what I did is I said, you know what? Let's get rid of this x because I don't want to have both an x and a y in my equation. If I replace it with that y plus 2, now all I have are y's in my equation. Well, if it's a single variable equation, we know how to solve that. So we're just going to solve to find the value of y. Put the y's together, you get 2y. If I want to get rid of the plus 2, I subtract 2 from both sides using the property of equality. And then I'm left with 2y equals 4. How do I get the y by itself? Well, when we want to get rid of a times 2, we divide both sides by 2, and we end up with y equals 2. Remember, our focus here isn't on solving equations today, so if this is problematic to you, you need to go back and watch some of our videos on solving equations because we really don't have time to talk about that right now. Now that we know that the y in both of these equations must be a 2, we can take either one of these original equations, replace the y with a 2, and find what the x is. Now, it really doesn't matter which of these two you pick. You tend to pick the one that seems easiest to compute. Since x is already by itself here, I'm going to take that second equation. Since I know that y is a 2, I'm going to replace the y with a 2. And that's, when I simplify that, that tells me that x is a 4. The solution to this system is the point 4, 2. Remember, if I were to graph this, this would have a line which would have an infinite number of possible combinations of x and y that would equal 6. If I were to graph this, it would have an infinite number of x's that where x equals y plus 2. It would form a line as well. But there's only one single point where those two lines are going to overlap or intersect, and that point is going to be the 4, 2. I can check that The same way we checked single variable equations earlier in the year, where I rewrite either one of the original problems. I plug in a 4 for the x and a 2 for a y, since that's what we said the solution is, and I just check to see if it's correct. As long as what comes out is true, I know my answer is right. Now, we did say that 4, 2 had to work in both equations, so I want to check the other one as well. If I put a 4 in for x and a y for 2, it does come out true. It's not too bad, is it? Let's try another one. Notice, up here I've got a system, y equals 5x and 3x plus 2y equals 52. They both have two variables in them, which means I can't just solve them the way we would have done in the past. Instead, what I notice is that this first equation already has a y by itself, and that y has the same value as 5x's. So what I'm going to do is I'm going to take this 5x and I'm going to plug it into the second equation for the y. There's the y. I'm going to replace it with 5x's because now I have a single variable equation that I can solve. 2 times 5x is 10x, 3x and 10x makes 13x. Divide both sides by 13, you get that y is a 4. That's the hard part of the problem, because once you know y is a 4, you can pick either one of these first two equations, plug the 4 in, and check to see what x would be. Since this is a shorter equation and the y is already by itself, I'm going to go ahead and plug it into that one. Notice that I got in a hurry and I plugged it in for x instead, so that's going to change the rest of this slide. My 4 should be over here. 4 equals... Okay, I'm going to back this up. Notice I have another system. Y equals 5x. And 3x plus 2y equals 52. Both equations in this system have two variables, so I can't solve them using the method we would traditionally use. However, when I look at this first linear equation, I notice that the y is already by itself. So what I'm going to do is I'm going to take anywhere I see that y in the second equation, and I'm going to replace that y with 5x's. See the y right here? I start off with my original equation. I'm going to take that y out and plug in 5x's. 2 times 5x is 10x, 3x and 10x is 13x, y is a 4. Notice that I accidentally got my variable wrong here. That's just a typo. We'll go back and fix that after we finish our recording. Now that I know that x is a 4, I can take either one of these equations, plug in the value we found for x, replace it with a 4, and we can solve to find out what y is. Since this first equation is shorter and the y is already by itself, I'm going to go ahead and use this one. I could have just as easily have used the other. I'm going to replace the x with the 4 because that's what we said should work, and it gives me y is a 20. Once again, this is what happens when you cut and paste. Your solution is 420. If we wanted to check those, we could. We don't really have time to do that here, but I can tell you 5 times 4 is 20, 3 times 4 is 12, 2 times 20 is 40, 12 and 40 make 52. This does indeed check out. Take a look over here. If you feel pretty comfortable, I would recommend that you pause the video and try this one on your own, then start the video to see if what you did makes sense. I'm going to go ahead and do this. I noticed that the second equation has the y by itself. I'm going to take it and plug it into the first equation for that y. There's your first equation. I'm going to replace the y with negative 2x plus 8 because it has the same value. And I'm going to simplify and get 8 equals 11. Now that's a problem, isn't it? 8 equals 11. Our variables have disappeared, and what's left is not true. Interesting. That's come up before when we were solving single variable equations. Do you remember what this means? If the variables disappear and what's left is not true, it means there are no solutions to this equation. We also said back when we talked about that, if the variables disappear and what's left is true, then there are an infinite number of solutions. So we would say that this system has no solutions. Do you remember from our graphing lesson what kind of lines or what kind of system has no solutions? Well, if I take this first equation and I rearrange it into slope-intercept form by subtracting 2x from both sides, notice I get y equals negative 2x plus 11. Compare that to the second equation. Do you see it? These lines have the same slope, but different y-intercepts. That means if you graph them, one's going to start at 8 and go down 2 every time. The other's going to start at 11 and go down 2 every time. And you're going to end up with lines that are parallel. We actually really like it when this happens because if we can see that there is no solution right from the beginning, then we don't have to do all this extra stuff where we find the second variable. Works out very, very nicely. Thought I'd throw one of those in for you just to keep you from, or to make sure you were aware of it so it didn't catch you off guard. Notice that if this had been something like 11 equals 11 and had been a true statement, we would have had infinite solutions. That means we would have had the exact same line drawn on top of itself. So it would be the same line written twice. A couple more things we need to talk about real quick. First of all, it is convenient when one of our variables is already by itself, but we can still do these if we have something like this. Notice you still have a system of two linear equations, but neither of them has a variable by itself. If this happens, you have to take the time to rearrange one of these equations so that one of the variables is by itself. When I look at this, I could rearrange it so this y is by itself, this y is by itself, this x is by itself, or this x is by itself. But I'm going to choose to get this x by itself. The reason for that is it has a coefficient of 1, which means it's going to be less steps to isolate that x. It also means that I'm far less likely to get some weird fractional answers, because sometimes that happens. If I want to get this x by itself, I have to get rid of this minus 2y. I'd use the property of equality to add 2y's to both sides, and I'd get x equals 2y plus 6. Notice now it looks just like our other examples. I'm going to take this second equation, and then I'm going to replace this x with a 2y plus 6 because those have the exact same value. And once again from there, it's just a little bit of algebraic computation, and you get y equals negative 2. Once you know that y is a negative 2, take either one of your original equations and plug that negative 2 in. Please don't stick it in the second equation or the equation you calculated, this version right here, because if you made a calculation error along the way and you substitute back into there, you may not catch that error. Always plug things back into the original equations. I chose the 3x plus 2y equals 2. I have no idea why I did that. I just liked it. I plug the negative 2 in for y. I get that negative 4. Add 4 to both sides. Divide both sides by 3, so x is a 2. The solution to this is 2, negative 2. Be careful. Some people forget to put the x first. Just because you found the x second doesn't mean it should go second in your parentheses. X always goes first. Last thing, these can appear as application problems as well. This is one, I believe, from the Big Ideas textbook, so thank you to those people for letting us use your problem. Hopefully you're okay with that. It says a drama club earns $1,040 from a production. A total of 64 adult tickets and 132 student tickets are sold. An adult ticket costs twice as much as a student ticket. Write a system of linear equations that represents the situation. And then here's the question. What is the price, if I can circle that, what is the price of each type of ticket? You'll remember back from our word problems or applications unit that the question is where we find our variable, or in this case variables, because it says what is the price of each type of ticket. So we know we're looking for two things. We're looking for the price of an adult ticket and we're looking for the price for a student ticket. Ordinarily, I wouldn't use S because my handwriting is so bad that my S's look like 5s, but since I've typed this out for you, I'm going to go ahead and use S because S reminds me of student ticket, just like A reminds me of adult ticket. I'm going to go back and read this again. A drama club earns $1,040 from the production. A total of 64 adult tickets and 132 tickets were sold. So we sold these tickets, and we earned this much money. That's a relationship. That's a story we can write into an equation. 64 adult tickets and 32 student tickets was a total of $1,040. Or, algebraically, if I take 64 times the price of the adult tickets, that's going to give me the total cost for adult tickets. Add that to 32 times the price of a student ticket, that's going to tell me how much was spent on student tickets. And I know it has to form a total cost of $1,040. That's the first equation in our system. Let's see what else it says. An adult ticket costs twice a student ticket. That's another relationship. The adult ticket costs twice as much as a student ticket. How do we write that? The cost of an adult is equal to 2 times the cost of a student. You now have a system. Here's equation number 1, and here's equation number 2. We're going to use the substitution method. Notice that if we did try and do this using the graphing method, we'd probably have some really weird and ugly numbers. Which one do you want to substitute in for what? Hopefully you realize that this already has A by itself. So we're going to plug that into the other equation here. I plugged it in, do a little algebraic solving. I can see that the student ticket is $6.50. Once you know the student ticket, you can take either one of these equations and plug the student price in and calculate the adult. It doesn't really matter which one, but hopefully you realize it's probably going to be less work to use the second one. So I plugged the student ticket in for that. The adult ticket was $13. And of course, we give our answer in a sentence because it is a word problem. Hopefully that's been useful to you, helpful to you. You may need to go back and watch it again if you struggle with that just a little bit. One thing I do want to make sure I point out that I didn't mention earlier is this. If you are going to substitute, you can never substitute something into itself. For example, I can't take this A equals 2s and substitute it into A equals 2s. Because if I were to do that, I would just always get 2s equals 2s. You always have to take whatever equation you're using to substitute and plug it into the other equation in order to get an answer that makes sense. As always, we do appreciate you taking the time to watch with us. Please go back and make sure you like and subscribe. Make sure you leave us a comment in the comment section. Also turn on your notifications so you can follow along with us as we are learning Algebra 1. Thank you again. Best wishes to all of you guys. Take care.